Hello and welcome. Tonight, I want to talk about a star you almost certainly know. It's a point of light that has defined our place in the cosmos for thousands of years. From a distance, it appears to be the most constant, most reliable star in the entire night sky. It's Polaris, the North Star. For centuries, it's been the anchor that has guided sailors across vast oceans and travelers across sprawling deserts. It's always there, fixed in the northern sky, a permanent beacon while every other star wheels around it. But here's the great irony. While we've used Polaris to find our way, scientists are discovering that the star itself is completely lost. From up close, Polaris behaves in bizarre and confusing ways that defy our scientific models. The closer we look with our most powerful instruments, the less sense it makes. It's a star that is so easy to see with the naked eye, yet it has become one of the most evasive and mysterious objects for our modern telescopes. So how can a star be so simple and so complicated at the same time? Today, we're going to dive into the problems with Polaris. We'll look at its hidden companions, explore its strange and unpredictable behavior, and reveal why this one star, our familiar North Star, could force us to redraw our entire map of the universe. First, let's get one thing straight. What you see as a single solitary point of light is not one star. It's actually a complex and dynamic system of 3 stars, all bound together by gravity. For most of human history, no one knew this. It wasn't until 1779 that the astronomer William Herschel, using a telescope, discovered that Polaris had a friend. He spotted a smaller, fainter star in a very wide orbit around the main one. We call this companion Polaris B, but the story didn't end there. Over a century later, in 1899, another astronomer noticed something odd about the main star. Its light showed a slight wobble, a change in its radial velocity, which suggested that something else was tugging on it, something much closer and invisible to telescopes at the time. It took until 1929 for spectroscopic studies to confirm this suspicion, but we didn't get our first actual picture of this third secret star until 2006, when the Hubble Space Telescope was finally able to resolve it. This tiny companion is called Polaris AB. So let's break down this family of stars. The main star, the one we actually see shining so brightly, is officially named Polaris AA. This is the star we think of as the North Star. It's an absolute giant, a yellow supergiant to be precise. It's about 5 times more massive than our Sun and a staggering 46 times wider. To put that in perspective, if you were to place Polaris AA in the center of our solar system, it would swallow Mercury's orbit whole. Orbiting this giant, at a distance of about 2.8 billion kilometers, is its close companion, Polaris AB. Together, these 2 stars, AA and AB, form a tight binary pair, completing an orbit around each other every 29.6 years. Then, much farther out, at a mind-boggling distance of 386 billion kilometers, is the third star, Polaris B. Its orbit is so vast that it takes about 40,000 years to go around the inner duo just once. Both of these companion stars, AB and B, are much fainter than the primary star, which is why they are so hard to see. Now, a triple star system is interesting, but that's not what makes Polaris a scientific headache. The real trouble starts with the main star, Polaris AA. It belongs to a very special and rare class of stars known as Cepheid variables. And as it turns out, Cepheid variables are one of the most important keys we have to mapping the entire cosmos. Back in 1908, an astronomer named Henrietta Leavitt made a monumental discovery while studying these stars. Cepheids are in a phase of their life where they physically pulsate, expanding and contracting, which causes them to grow brighter and dimmer in a perfectly regular, predictable cycle. Leavitt found a direct, unshakable relationship between how long a Cepheid's pulsation period lasts and how bright the star truly is, its absolute luminosity. The rule was simple. The brighter the star, the longer it took to complete one cycle of pulsation. This discovery was revolutionary. It turned Cepheids into what astronomers call standard candles. Think of it like a light bulb. If you know you're looking at a 100-watt bulb, you can tell how far away it is just by how dim it looks. Leavitt's discovery meant that if we could measure the pulsation period of a Cepheid, we would know its true wattage. Then, by measuring how bright it appears to us here on Earth, we could calculate its distance with incredible accuracy. This technique became a crucial rung on the cosmic distance ladder, our method for measuring the vast distances of the universe. Before this, we were limited to measuring stars only a few hundred light years away. But with Cepheids, we could suddenly measure distances of millions of light years, reaching out to other galaxies. And by the way, if you're enjoying how we break down these huge cosmic ideas, this is exactly what we do here at Space Science Simplified. We take the biggest, most complex mysteries in the universe and make them easy for anyone to understand. So if you're curious about the cosmos and want to learn more, take a second to hit that subscribe button so you don't miss our next exploration. It really helps the channel out. Okay, back to the cosmic ladder. We use closer methods to calibrate the Cepheids, and then we use the Cepheids to calibrate even more distant markers, like certain types of supernovae. As the closest Cepheid to Earth, Polaris should be the absolute gold standard for this entire system. It should be the anchor point, the rock upon which we build our measurements of the size, age, and expansion of the universe. But this is where everything starts to go wrong. It turns out, Polaris is a very weird Cepheid. For starters, its pulse is erratic. For about 150 years, astronomers observed that its pulsation period, which is around 4 days long, was getting longer by about 4.5 seconds every single year. For a Cepheid, that is an incredibly fast rate of change, suggesting the star is evolving very quickly. But then, just as astronomers were trying to build theories to explain this rapid change, Polaris threw another curveball. Around the year 2010, the trend suddenly and inexplicably reversed. Its period started getting shorter, year after year, and nobody knows why. It's not just the timing of its pulse that's strange, it's the strength of it too. The difference between its brightest and dimmest points, what astronomers call its amplitude, was steadily declining for decades. It got fainter and fainter until the 1990s, leveled off for a bit, and then started to creep back up again. This pattern of fading away and then reviving has never been seen in any other Cepheid star. One theory is that Polaris might be in a very rare and unstable phase of its life. Most of the Cepheids we see are in a relatively stable phase of their evolution, but there's an earlier phase. Right after a star leaves the main sequence and begins its journey to becoming a red giant, that is incredibly brief and not well understood. Catching a star in this first unstable phase is extremely rare, but it could explain some of the bizarre behavior. The problem is there's no consensus. Some scientists argue it must be in this first phase, while others are convinced it's in a much later one. As if its unpredictable pulse wasn't enough of a problem, there's something even more fundamental that we can't seem to figure out. Something embarrassingly simple. Its distance. You would think that with all our modern technology, measuring the distance to our own North Star would be straightforward. But it's brutally challenging. Because Polaris is so bright, it tends to saturate the sensitive detectors on our best telescopes, making the readings unreliable. It's like trying to take a detailed photograph of a stadium light from 10 feet away. You just get a white glare. On top of that, because it's hundreds of light years away, the parallax shift we use to measure distance is unimaginably small. Over the years, estimates for its distance have been all over the map, ranging from as close as 323 light years to as far as 520. That is a massive range of uncertainty. The European Space Agency's Hipparcos mission in the 1990s placed it at 434 light years. The more recent and powerful Gaia mission has given us a figure closer to 447 light years. But without a precise, universally agreed-upon number for its distance, all of our other calculations about Polaris, its true mass, its actual size, its intrinsic luminosity, are built on a shaky foundation. And this leads to the next major headache. The estimates we do have for Polaris's properties simply don't match our models of how stars are supposed to evolve. For example, based on its pulsation, AA appears to be much less massive than our theories predict for a star of its type. This isn't just a small error, it's a significant discrepancy. It suggests that our fundamental understanding of stellar physics might be missing something crucial. Perhaps the models are too simple and don't properly account for factors like stellar rotation or mass loss from strong stellar winds. Recent observations in 2024 even detected giant star spots on its surface, hinting at a magnetic field that could be interfering with its pulsations in ways we don't yet understand. If our models are wrong for our closest Cepheid, it casts a shadow of doubt on our measurements across the entire universe. It could mean our cosmic distance ladder has a broken rung right at the very bottom. But the mysteries don't stop there. Perhaps the most perplexing puzzle of all is the age gap. If Polaris AA and Polaris B are gravitationally bound together in the same system, they almost certainly should have formed from the same cloud of gas and dust at the same time. This means they should be the same age. However, our observations tell a completely different story. Based on its properties, the main star, Polaris AA, appears to be a relatively young 50 million years old. But estimates for its distant companion, Polaris B, put its age at around 2 billion years old. That's not just a small difference. It's an enormous, seemingly impossible age gap. So what happened here? One radical theory is that Polaris B isn't actually a companion star at all, just a star that happens to be in our line of sight. But the evidence for them being a true gravitationally bound system is quite strong. A more intriguing idea is that Polaris AA is something called a blue straggler. We see these in dense star clusters, stars that appear much hotter, bluer, and younger than their neighbors. The leading theory is that these stars are the result of stellar mergers, where two older, smaller stars in a close binary system collide and merge into one. The result is a new, more massive star that has been rejuvenated with fresh fuel, making it appear artificially young. It's possible that this is what happened to Polaris AA. While this merger hypothesis is speculative, it shows just how much this single star system challenges our understanding of how stars form and evolve. In the end, Polaris has guided humanity for millennia across oceans and continents. But today, it's guiding us in a different way. It's guiding us to the very edge of our scientific knowledge and forcing us to confront what we still don't know about the stars and the universe. The problems with Polaris have huge implications. If we can't trust our measurements of our closest Cepheid, how can we be sure about our measurements of galaxies millions of light years away? This uncertainty directly impacts one of the biggest debates in modern cosmology, the precise rate of the universe's expansion. And just like its strange behavior, Polaris's role as our guide is also temporary. The Earth's rotational axis has a slow wobble, much like a spinning top. This means that over a cycle of 26,000 years, our celestial North Pole traces a slow circle through the sky, pointing to different stars. About 14,000 years ago, the North Star was the bright star Vega. And in about 12,000 years from now, our axis will have wobbled back, and Vega will be the North Star once again. For now, Polaris remains our anchor in the night sky. But for scientists, it is a beacon of a different kind, one that illuminates the gaps in our understanding. So the next time you look up and find that steady, unwavering point of light in the north, remember that you're looking at one of the greatest and most fascinating puzzles in the cosmos. If you loved unraveling this mystery with us today, please do us a huge favor and subscribe to Space Science Simplified. We post new videos every single week, diving into everything from the secrets of black holes to the search for alien life, all explained in a way that anyone can understand. Make sure to hit that notification bell so you're the first to know when our next video drops, and let us know in the comments what cosmic mystery you think we should simplify next. Thanks for watching and keep looking up.